Have you ever found yourself wondering what really governs the unpredictable events that swirl around us every single day? From the simplest coin flip to the dizzying complexity of stock market shifts, or even how a virus spreads through a population chance, it seems, is just everywhere. But what if we told you there's this incredibly clever mathematical toolkit that helps us make sense of the messiness of chance? It allows us to understand, quantify, and even predict these seemingly random occurrences.
It's a powerful idea, isn't it? That beneath the surface of apparent chaos, there are these underlying patterns and rules, and we can not only discover them, but actively work with them. It's truly about bringing a scientific lens to the realm of uncertainty, transforming guesswork into informed insight.
Exactly. And today we're taking an extremely long, deeply detailed deep dive into some truly insightful lecture notes on probability. Our mission for you is to extract the most important nuggets of knowledge, giving you a serious shortcut to being well informed about the fundamental concepts of probability theory and stochastic processes. We're going to unpack surprising facts, explore real-world applications, and, connect the dots in ways that will fundamentally change how you view uncertainty. Get ready for some serious aha moments because this deep dive is going to be an illuminating ride into the heart of randomness. To really understand chance, we first need to speak its language, and that starts with defining what we're actually observing. At the very core of probability, the foundation for everything, is this idea of an experiment. Now, when we say experiment, we're not necessarily talking about like a lab in a white coat. We mean any process whose outcome isn't known in advance. The key here, the really crucial part, is that while you can't predict what will happen, you can know the complete set of all possible things that could happen.
That's right. And this complete set of all possible outcomes is what we call the sample space, often denoted S. Think of it as the entire universe of possibilities for your experiment. Defining this sample space accurately is, well, it's the first critical step in any probabilistic analysis. It literally sets the boundaries for everything else.
And it sounds simple, but this sample space can vary wildly. For example, a simple coin flip. What's the sample space there?
Just two outcomes, heads or tails, HT.
Right. That's a discrete set, meaning we can count the distinct possibilities, easy. Or rolling a standard six-sided die, the sample space expands a bit, right, to 1, 2, 3, 4, 5, 6.
Exactly. Still discrete, still countable, but with more possibilities. But here's where it gets truly interesting and broadens our perspective. Consider measuring the lifetime of a car. What's the sample space for its lifespan?
Okay. It's not just like 5 years or 6 years. It could be anything in between.
Precisely. It's continuous. It could be 5.37 years or 7.001 years or any value within an interval. Here, the sample space consists of all non-negative real numbers. We represent that as starting from 0 and going to infinity, so 0C.
Right, zero shift. And that shift from discrete to continuous, it shows just how broadly applicable these core concepts are. It goes way beyond simple games.
Absolutely. It extends into real-world phenomena like product longevity, time measurements, all sorts of measurable quantities.
Okay, so we have our sample space, our universe of what could happen. Now, within that universe, we often want to focus on something specific. This brings us to the concept of an event. An event is simply any specific outcome or maybe a collection of outcomes that you're interested in. It's a subset of that larger sample space.
Let's revisit our examples to clarify this. For the coin flip, if we define an event E as getting a head, then E is just H, simple. For the die roll, if E is getting a 1, then E won. But we can also define an event as a collection. If E is the event of getting an even number, then E would be the set 2, 4, or 6.
Got it. So an event isn't always just one single outcome. It can be a group of them.
Exactly. That's a key point.
Once we understand experiments, sample spaces, and events, we can start to lay down the basic rules of probability. These are the fundamental axioms that govern how probabilities behave. One of the first rules, and one you'll use constantly, is about combining events. For any two events, say E and F, the probability of E or F occurring, that's PE union F, is given by adding their individual probabilities, PU plus PF, and then subtracting the probability of both E and F occurring simultaneously. We call that overlap, PE intersect F, or sometimes just PEF.
And that subtraction of PEF is absolutely critical. It accounts for any shared outcomes between E and F, ensuring they aren't counted twice.
Right, avoids double counting.
Now, if events E and F cannot happen at the same time, meaning their intersection is empty, there's no overlap, then they are called mutually exclusive. In this special case, PE union F simplifies nicely to just PE plus PF, because there's no overlap to subtract. And naturally, the probability of an impossible event, like rolling a 7 on a 6-sided die, is always 0. PA equals 0.
What's also really foundational and makes many initial calculations much simpler is the concept of equal likelihood.
Hmm.
Imagine tossing two coins. The sample space, as we mentioned, is four possibilities, HHT, THTT.
Right, 4 outcomes.
If each of these four outcomes is equally likely, which seems reasonable for fair coins, then each has a probability of 14. This assumption of equal likelihood, when it applies, is a powerful tool for assigning initial probabilities. It's a great starting point for many models.
Building on these basic rules, we encounter another cornerstone concept, independence. Intuitively, events are independent if knowing whether any of them occurred has no effect whatsoever on the probability of any other event.
Like they don't influence each other at all.
Exactly. This intuitive understanding is frequently used in modeling, and it's a powerful simplifying assumption. Formally, for independent events, the probability of their joint occurrence, say PE1 and E2 and ER, is simply the product of their individual probabilities, PE1, PE2, PER.
Okay, multiplication rule for independent events. Makes sense. Now here's where we hit a truly surprising and critical insight that can trip people up, and the lecture notes highlight it beautifully. It's the distinction between what we call pairwise independence and full independence. You might think they're the same thing.
But they're not always. And this example is crucial for anyone building models. Imagine an urn with 4 balls, numbered 1, 2, 3, 4. Let's assume drawing any ball is equally likely, so probability 14 for each.
Okay, 4 balls, 14 chance each.
Now define 3 events. Event E is drawing ball 1 or 2, so PE equals 24 equals 12. Event F is drawing ball 1 or 3, PF. And event G is drawing ball 1 or 4, PG equals 12.
Okay, E12, F13, G14. Each has a 12 probability. So far, so good. Now, let's check for independence between pairs of these events. What's the probability of E and F? That means drawing ball 1.
Right, the intersection EF is just 1, so PEF...
Because NPE multiplied by PF is 12. 12, 14.
Yeah.
Hey, they match. So E and F are pairwise independent.
Good. Now check EG. The intersection EG is also just 1, so PEG 14.
PBG, 12. 12, 14. They match too. E and G are pairwise independent.
And finally, F and G.
Intersection FG is 1 again, PFG 14, and PFPG rules 12. Okay, so F and G are also pairwise independent. It seems like all 3 events are independent of each other.
But here's the kicker. The powerful insight, the twist. While E, F, and G are pairwise independent, they are not fully independent.
Wait, how? They all seem independent in pairs.
Because full independence requires more. It requires that the probability of all 3 happening, PEFG, must equal the product, PE, PF, PG.
Okay, let's check that. What's the event, EFG? It means E happens, and DF happens, and DG happens. That only occurs if we draw ball 1.
Exactly. EFG, PFG equals 14.
Right, but what's product PE, PF, PG?
T 12, 12, 18.
Ah, 14 is definitely not equal to 18.
Precisely. So these events are not fully independent. The crucial lesson here, the aha moment, is that pairwise independence does not guarantee full independence. If you assume full independence in your model just because pairs are independent, you could be making massively incorrect predictions. It's a subtle but critical distinction.
That is subtle. Wow. Okay, so always check the full condition, not just pairs. Got it.
That's a really important point, and it perfectly sets the stage for our next major topic, conditional probability. Because often, in the real world, we don't operate in a vacuum of perfect ignorance, right? We gain new information about an experiment's outcome, and that new information fundamentally changes the odds. Conditional probability is all about updating our beliefs and calculating probabilities given this new knowledge. Precisely. The core idea is that knowing one event occurred can drastically alter the likelihood of another. When we talk about the probability of event E occurring, given that event F has already occurred, we write it PEF. We're essentially narrowing our focus. We're saying, okay, we know F happened, so let's recalculate the chances of E within this new, smaller reality.
So the universe of possibilities kind of shrinks.
Exactly. The definition reflects this. PEF is the probability of both E and F happening, PEF, divided by the probability of F happening, PF, assuming PF isn't 0, of course.
Let's use a classic example to really cement this. Imagine you're rolling 2 fair dice. The initial sample space has 36 equally likely outcomes, right? All the way to 6, 6.
Correct. 36 outcomes.
Now, what's the probability that the sum of the 2 dice is 6, given that the first die is a 4?
Okay. Without that extra info that the first die is a 4, the outcomes that sum to 6 are 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. 5 possibilities out of 36.
Right, 5, 36.
Yeah.
But now we add the condition. The first die is a 4.
Exactly. Once we're given that the first die is a 4, our possible outcomes are immediately narrowed down. The sample space effectively shrinks. We are now only considering the outcomes where the first guy is a 4. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6.
Ah, so there are only 6 possibilities left in our new restricted sample space.
That's right. And since each of those 6 outcomes was originally equally likely, they remain equally likely within this new space. Out of those 6, only one gives us a sum of 6. The outcome, 4.
So the conditional probability P sum 6 first die 4 is just 1 out of 6.
Precisely, 16. It demonstrates vividly how new information reshapes our universe of possibilities and changes the probabilities.
Okay, that makes sense. Now, building on conditional probability, we arrive at something truly fundamental, Bayes' formula. You hear this mentioned a lot. What's the core idea?
Bayes' formula is a cornerstone of modern probability and statistics, really.
Mm.
Its core idea is incredibly powerful. It allows us to reverse the conditioning. Instead of asking for P effect cause, it lets us find P cause effect.
So you flip the question around based on what you observe.
Exactly. It's fundamentally about updating our initial beliefs, our prior probabilities, with new evidence, the observation or effect, to arrive at a more informed posterior probability for the underlying cause.
It sounds like it helps you reason backwards from evidence.
That's a great way to put it. Let's take a relatable example, the multiple choice test scenario from the notes.
Right.
A student takes a test. For any question, they either know the answer, say with probability P, or they guess with probability 1P. If they guess, and there are M choices, they're correct with probability 1 meter.
Right. Random guessing.
Now, the crucial question Bayes helps answer is, what's the conditional probability that the student knew the answer, given that they answered it correctly? We observe they got it right. What's the chance they actually knew it?
Ah, so P, no, correct. How does Bayes help?
Bayes' formula provides the structure. It says P no correct equals P correct no times P no, divided by the total probability of being correct. The total probability of being correct comes from 2 paths. Either they knew it and were correct, T, P no, or they guessed and were correct, P correct guess, P guess.
Okay, so the numerator is the path we're interested in, knowing and being correct, and the denominator is the sum of probabilities for all paths that lead to being correct.
Precisely. We know P correct no is 1. If you know it, you get it right. We know P no is P. We know P correct guess is 1 meter, and P guess is 1P. Plugging those in gives us the updated probability that they knew it, given the correct answer. It quantifies how much the evidence, correct answer, increases our belief they knew it.
That's really useful, inferring the underlying state, knowing from the observation, correct answer, very applicable.
And it goes further. Consider another example, the lost letter in folders. You know, a letter is equally likely to be in any of 3 folders. So prior probability is 13 for each folder. Let's say there's a probability, alpha, that you'll actually find the letter if you look in folder I and it's actually there. Alpha might be less than 1, maybe your search isn't perfect.
Right, you might miss it, even if it's there.
Now, the scenario. You look in folder 1 and don't find the letter. The question is, what is the probability that the letter is still in folder 1? P, letter in folder 1, didn't find in folder 1.
Intuitively, you might think, well, I looked there and didn't find it, so the probability should go down, right? Maybe quite low.
Yeah, it probably does go down. But Bayes' formula gives the precise update. The observation is didn't find in folder 1. Bayes considers the probability of not finding it given it was there, which is 1 alpha 1, and the probability of not finding it given it wasn't there, which is 1 since you can't find what isn't there. It weighs these possibilities by the prior probabilities, 13 each, to give you the new posterior probability that it's still in folder 1 given your failed search. Even a failed observation provides valuable information.
I see. It accounts for the chance you just missed it. That's clever.
For a final, very practical application, the lecture notes include that classic exercise about colorblindness. 5% of men and 0.25% of women are colorblind. A randomly chosen person is equally likely to be male or female. Given the person is colorblind, what's the probability they are male?
Ah, yes. P-male colorblind. Another Bayes application.
Exactly. This is a direct, real-world application in diagnostic or population-level analysis. We observe colorblindness, the effect, and want to infer the probability of the likely underlying characteristic, male in this case due to the higher base rate. It's vital in medicine, genetics, risk assessment, anywhere you need to rigorously update beliefs based on observed evidence.
Okay, moving from the rules of probability and how information updates our beliefs, we need a way to link these abstract outcomes, heads, tails, drawing ball, 1 to numbers, things we can actually measure and, compute with.
That's where random variables come in. It sounds fancy, but at its core, a random variable is simply a function. It assigns a numerical value to each possible outcome in the sample space.
So it's the bridge from abstract outcome to measurable quantity, like heads becomes number of heads equals 1.
Exactly. It quantifies the randomness, and these random variables generally fall into two main types. Discrete random variables take on a countable number of values, like the number of heads in 10 coin flips, 0, 1, 2, up to 10, or the number rolled on a die, 1, 2, 3, 4, 5, 6.
Okay, countable values.
Then there are continuous random variables. These can take on any value within an interval, like the exact lifetime of that car we mentioned or the temperature in a room. Think of it as whole numbers versus anything on a sliding scale.
Got it. Discrete is counting, continuous is measuring. Now, how do we describe the probabilities associated with these values?
For discrete random variables, we use a probability mass function, or PMF, often written as Px. This function simply tells you the probability that the random variable x takes on a specific value x. Px yields x.
So P1 would be the probability of rolling a 1 on a die, 16.
Exactly. For continuous variables, it's slightly different. We use a probability density function, or PDF, written fx. This function describes the relative likelihood for the random variable to take on a given value. It's not a probability itself. You find actual probabilities by looking at the area under this density curve over a certain interval.
Ah, so PAXAB is the integral of fx from a to b.
Precisely. For instance, for a uniform random variable that's equally likely to be any value between 0 and 1, its PDF is just fx1 over that interval. The probability that x falls between a and b, where 0a, a, b, a1, is the integral of 1 from a to b, which is just ba, the length of the interval.
Okay, PMF for discrete, PDF for continuous, giving density, need to integrate for probability. Once we can assign numerical values, we can start talking about their expected behavior, right? Like what happens on average.
Exactly. This leads us to the concept of expectation, or the mean, often denoted EX. The expected value of a random variable is essentially a weighted average of all its possible values, where each value is weighted by its probability, or density.
So it's like the long-run average outcome if you could repeat the experiment many, many times, what you'd expect on average.
That's the perfect intuition. For discrete random variable x, you calculate EX by summing up each possible value x multiplied by its probability, px. Sum of xpx.
And for continuous integration again?
Yep. For continuous variable x with density fx, Ex is the integral of x multiplied by its density fx over all possible values, integral of x, fx, dx. It's the continuous version of that weighted average.
Okay, let's look at some examples. The lecture notes mention expectations for common distributions, like the binomial.
Right, the binomial random variable. If x counts the number of successes in n independent trials, each with success probability p,
Yeah.
then the expected number of successes Ex is simply n times p.
EX into P. That feels very intuitive. Flip a fair coin, P 0.5, 10 times into P10, you expect 2.5 instead of 5 heads.
Exactly. And while it feels intuitive, the lecture notes actually show a quite elegant mathematical derivation involving manipulating sums. It shows the rigor behind the intuition.
What about the uniform distribution? Say, uniformly random between alpha and beta.
For a uniform random variable on the interval, the expected value is simply the midpoint, alphas of +2.
Also very intuitive. Pick a number randomly between 0 and 10, you expect the average to be 5.
And then there's the exponential random variable with a rate parameter, lambda. This distribution is crucial for modeling waiting times. Think how long until the next bus arrives or the next radioactive decay event. Its expected value is simply 1.
EX equals 1. So if events happen at a rate of little 2 per hour, the expected waiting time between events is 12 hours.
Precisely. These examples show how expectation gives us a single number, a central tendency, capturing the average outcome for different types of random phenomena.
But the average doesn't tell the whole story, does it? Like two data sets could have the same average but be spread out very differently.
Absolutely right. The mean tells you the center, but it doesn't tell you about the spread or dispersion. That's where variance, denoted varx, comes in. Variance quantifies how spread out a random variable's values typically are from its mean, Ex. Mathematically, it's the expected value of the squared difference between the variable and its mean. Varx equals its obus.
So a low variance means values cluster tightly around the mean, more predictable.
Exactly. High predictability. While a high variance means values are widely scattered, indicating much more unpredictability or risk, think of a dart player. Low variance means their darts land close together, even if off-center. High variance means they're all over the board.
Okay, mean for center, variance for spread. Got it. Now, the notes move into some really profound theorems about aggregates of random variables. The central limit theorem, CLT.
Ah, yes. The CLT. This is arguably one of the most profound and frankly magical theorems in all of probability and statistics. What it
Yeah.
tells us is astonishing. Take a large number of independent and identically distributed random variables.
Okay, lots of random things, all drawn from the same hat, independently.
Right. The CLT says that their sum, or their average, regardless of what their individual distribution looks like, it could be uniform, exponential, weird, whatever.
Regardless. Really?
Yes, provided they have a finite variance. Their sum, or average, will tend to be approximately normally distributed. The bell curve emerges.
That's incredible. Why does that happen? Why the bell curve?
It's truly remarkable. The heuristic proof in the notes uses something called moment-generating functions. Essentially, when you combine the generating functions of many independent variables, the result converges mathematically to the generating function of a normal distribution. The core insight is that when you average many independent random fluctuations, the extremes tend to cancel each other out, and the result clusters around the mean in that specific bell shape.
So it explains why so many things in nature follow a bell curve, like heights, measurement errors.
Exactly. It's because these things are often the result of many small, independent contributing factors adding up. The CLT guarantees the aggregate result will look normal. This is fundamental for statistical inference. It lets us make approximations and calculate probabilities for sums or averages even if we don't know the original distribution. The notes mention approximating probabilities for sums of Poisson variables using the normal distribution, a direct application.
Amazing. And closely related is the strong law of large numbers, SLLN. How is that different?
Good question. While the CLT describes the shape, the distribution of the average, it becomes normal, the SLN describes where the average goes in the long run. The SLN states that with probability 1, meaning almost surely, the average of a sequence of independent and identically distributed random variables converges precisely to their expected value as the number of variables goes to infinity.
So the average eventually becomes the expected value.
Yes, it formalizes our intuition. Flip a fair coin enough times, the proportion of heads will eventually settle at 0.5. It's not just likely. The SLLN says it happens with probability 1. The notes mention the proof involves some subtleties needing more than just basic inequalities like Chebyshev, sometimes using subsequences via the Borel-Cantelli lemma. But the implication is profound.
It underpins things like insurance, right? The insurance company knows that over millions of policyholders, the average claim amount will converge to the expected value, allowing them to set premiums.
Precisely. It also underpins gambling odds, long-term investment returns, and any situation relying on long-run averages. The notes explicitly mention the limiting proportion of time an event E occurs being PE as a direct consequence. It's the mathematical guarantee behind the house always wins, if odds are set correctly, or why empirical frequencies match theoretical probabilities over time.
Okay, so far we've handled single events, averages, spreads, even the convergence of averages. But reality isn't static, right? Things evolve over time. One state leads to another. How do we model randomness in motion?
That brings us to the fascinating world of stochastic processes. A stochastic process is essentially a collection of random variables indexed by time. It's a mathematical way to describe how a system evolves randomly over time. Think xt, where air represents time.
And time itself can be viewed differently here.
Exactly. Time can be discrete or continuous. A discrete time process means we look at the system at distinct points in time, like xn, n, 0, 1, 2, air. Think daily stock prices or the number of customers at the end of each hour.
Okay, snapshots in time.
A continuous time process means the system can change at any instant, this Kyoto-yoge, like the temperature fluctuating or the position of a particle undergoing Brownian motion. And every process has a state space, which is simply the set of all possible values that the random variables xn or xt can take on. It could be discrete, number of machines broken, or continuous voltage level.
Got it. Now, within this huge field of stochastic processes, there's a particularly important type mentioned prominently in the notes. Markov chains. What makes them special?
What makes Markov chains special and incredibly useful is the Markov property. It's essentially a property of memorylessness.
Memorylessness, like it forgets its past.
Precisely. For a Markov chain, the future state of the system depends only on its current state and not on how it got there. Given the present state, the past is irrelevant for predicting the future step.
So if a system is in state I right now, to predict where it goes next, I only need to know it's in state I. I don't need to know if it came from state J or state K before that.
Exactly. It's like that person with perfect short-term memory but no long-term recall of their journey. This memoryless property drastically simplifies the analysis. The evolution is governed by transition probabilities, usually written PJ. This is the probability of moving from state I to state J in one step, or one unit of time.
Okay, PJ is the one-step probability from I to J. What about longer term? Like probability of going from I to J in, say, 5 steps.
That's where the Chapman-Kolmogorov equations come in. They provide a way to calculate multi-step transition probabilities from the one-step probabilities. Essentially, the probability of going from I to J in n plus m steps can be found by summing over all possible intermediate states k that the process could be in after n steps. It's like multiplying transition matrices together, Pn plus m, pre-also Pm.
Right, matrix multiplication captures these path probabilities, and the applications seem really broad.
Incredibly diverse, they pop up everywhere. In genetics, modeling the state, like genotype, across generations, the Hardy-Weinberg law is related. In manufacturing, analyzing production lines, machine reliability, quality control. In physics and computer science, random walks are fundamental Markov chains. Think of the gambler's rune problem. A gambler's fortune fluctuates randomly until they hit a target or go broke.
That's a classic Markov chain.
It is. Or probabilistic algorithms for solving complex problems, like satisfiability, SAT. The notes specifically mention the symmetric random walk and its property of being recurrent, meaning if it starts at the origin, it's guaranteed, with probability 1, to return eventually.
Wow, guaranteed return. Okay, and MCMC.
Yes. Markov chain Monte Carlo, MCMC, is a huge area. It uses cleverly constructed Markov chains to simulate and sample from extremely complex probability distributions, especially in Bayesian statistics, where direct calculation is impossible. And then there are Markovian decision processes, MDPs, which provide a framework for making optimal decisions sequentially in environments where outcomes are uncertain but depend on the current state and the action taken. Used a lot in reinforcement learning and operations research.
Let's try to make it concrete with that hotel check-in example from the notes. It seemed like a good illustration.
Okay, so at the start of a day, there are I families in the hotel, state I. Each of these I families decides independently whether to stay another day, say with probability Q, so they leave with probability P equals 1Q. Simultaneously, new families arrive throughout the day, and the number of new arrivals follows a Poisson distribution with mean A.
So two things happening. Some families stay, some new ones arrive. We want the probability of ending up with J families tomorrow, PJ.
Exactly. To calculate P, you need to consider all the ways it can happen. Suppose K of the original I families decide to stay. The probability of this is given by the binomial distribution, K successes out of I trials, probability Q. Then, for the final state to be J, you must have exactly JK new families arriving. The probability of this is given by the Poisson distribution with mean A.
So P involves summing up the products of these binomial and Poisson probabilities over all possible numbers of families staying, K from 0 to I.
Precisely. PJ equals sum over K. P is stay, I start. PJK arrive. It combines the retention and arrival processes. It can get complex, but the Markov framework structures it.
What about the expected number of families tomorrow, EXN xn1 equals I? Does that simplify?
It does nicely. The expected number of families staying from the original I is simply IQ, using the binomial expectation. The expected number of new families arriving is simply I, the mean of the Poisson. Since expectation is linear, the total expected number tomorrow, given I today, is EXN xn1 equals I equals IQ plus.
IQ plus us. That's elegant. It clearly shows the contribution from retained families, IQ, and new arrivals. Very intuitive.
It is. Now, another fascinating concept for some Markov chains is time reversibility.
Time reversibility, like running the process backwards.
Sort of. Imagine you record the sequence of states the chain visits over a long time. If the chain is time reversible, the statistical properties of that sequence will look exactly the same if you played the recording backward. It means in statistical equilibrium, the rate of flow from state I to state J is equal to the rate of flow from state J back to state I.
Not all Markov chains have this property, I assume.
No, it's a special condition. It's often related to detailed balance equations. If pi is the long-run limiting probability of being in state I, and key is the instantaneous transition rate from I to J for continuous time, the condition is pi key Kachela key.
Okay, a balance condition. Why is it useful?
Because if a chain is time reversible, satisfying these detailed balance equations often makes it much, much easier to find the limiting probabilities.
Pi.
You might be able to solve for the pi's directly from the balance equations, instead of solving a large system of linear equations for the overall equilibrium.
The notes mentioned a machine repair example.
Yes, a classic application. Imagine machines, each breaking down at radii, and a single repair facility sixing machines at radii when working on machine I. Maybe the repair person works faster on certain machines. When right machines are down, the repair effort might be shared, so each gets repaired at weight on a total K or something similar. This system's state could be which machines are currently broken. Finding the long-run probability of having, say, 3 specific machines down can be very complex. But sometimes, under certain assumptions about the rates, the system is time reversible, and the detailed balance equations greatly simplify finding these steady-state probabilities. It gives insights into system availability, bottlenecks, etc.
Okay, so Markov chains, model state transitions, often with memorylessness. Now let's shift focus slightly to another type of process that's incredibly important. Processes that just count events over time.
Right, counting processes. As the name suggests, a counting process, let's call it NPT, simply tracks the total number of events that have occurred up to time t.
Like number of emails arrived by noon or number of customers entering a shop by 3 p.m.?
Exactly. These processes have some basic properties. NT must be non-negative, can't have negative counts, and integer valued. It must be non-decreasing. Counts only go up, events don't unhappen. And importantly, the difference NT for ST represents the number of events that occurred strictly in the interval.
Makes sense. And a key property mentioned is independent increments.
Yes, that's crucial for many useful counting processes, especially the Poisson process. Independent increments means the number of events occurring in non-overlapping time intervals are statistically independent. So the number of cars passing between 9:00 and 9:10 a.m. has no influence on the number passing between 10:30 and 10:45 a.m.
Okay, which brings us to the star.
Yeah,
Poisson process.
Yeah.
What defines it seems to come up constantly.
it really does. The Poisson process with a constant rate bureau is a counting process that satisfies 3 key axioms beyond the basic definition. 1. It starts at 0. N0, x0 at 0, no events at the very beginning. 2. It has stationary and independent increments. Stationary means the probability of a certain number of events depends only on the length of the time interval, not on when the interval occurs. The rate is constant, and increments are independent, as we just discussed.
Okay, starts at 0, constant average rate. Events and disjoint intervals are independent. What's the third axiom?
The third one nails down the local behavior. It says 3a. The probability of exactly one event occurring in a very short time interval of length h is approximately a. More precisely, it's O plus O, where O means terms that go to 0 faster than h itself. 3b. The probability of more than one event occurring in that same tiny interval h is negligible. It's O.
So in tiny intervals, you basically get either 0 events, most likely, or exactly one event, with probability proportional to O and the interval length. Multiple simultaneous events are essentially impossible.
Exactly. Events happen one at a time, continuously, at an average rate nu, but randomly.
Now, the notes stress a deep connection between the Poisson process and the exponential distribution.
A fundamental connection. If you have a Poisson process with rate no, the time between consecutive events follows an exponential distribution with mean 1. And conversely, if the times between events are independent and exponentially distributed with mean 1, the counting process itself is a Poisson process with rate no. There are two sides of the same coin.
So if emails arrive according to a Poisson process at a rate no equals 6 per hour, the time between emails is exponentially distributed with a mean of 1/16 of an hour, or 10 minutes.
Precisely. This link is incredibly useful for analysis. It also leads directly to the probability mass function for the Poisson process. The probability of observing exactly n events within a fixed time interval of length is given by the Poisson distribution formula, Pn, At, and An.
Okay, so the number of events in a fixed time tem follows a Poisson distribution with mean O. Makes sense. The longer the interval, the more events you expect on average.
Correct. And the applications are incredibly rich, as the notes show. For instance, in analyzing greedy algorithms, sometimes the cost or value associated with steps in an algorithm can be modeled as arriving according to a Poisson process, helping analyze the algorithm's average performance.
Or that minimizing highway encounters problem. Sounds abstract.
It might be modeling cars on different lanes as independent Poisson processes and calculating probabilities being side by side. The coupon collecting problem is another great example. Collecting coupons is usually tricky because getting the last few depends heavily on what you already have.
Right, dependencies make it hard.
But the notes suggest a clever trick. Imagine coupons arrive according to a Poisson process over time. If there are different types of coupons, arriving with proportions pj, then the arrivals of each specific type can be modeled as independent Poisson processes with rates up j's. This independence makes it much easier to analyze things like the time needed to collect at least one of each type. It becomes finding the maximum of several independent processes.
That is clever. Using the Poisson framework to break the dependence. What about the AIDS tracking example?
That likely refers to epidemiological models where, say, NT represents the number of individuals infected but still asymptomatic by time t. Observable data, like diagnoses, might be linked back to this underlying unobservable Poisson-like process for infection spread, allowing estimation of the rate or.
And the conditional distribution of arrival times.
Yeah.
That sounded interesting.
It's a remarkably beautiful result. Suppose you know that exactly n events of a Poisson process occurred between time 0 and time t. So nt, nd, the theorem says that given this information, the actual times at which those n events occurred, t1, t2, tn, are distributed exactly as if you took n independent random variables uniformly distributed over the interval 0 at tn, and then simply sorted them in increasing order.
Wow, so conditional on the total count, the locations of the events are just uniformly scattered.
Exactly. It's incredibly intuitive and powerful for understanding the internal structure or simulating the process conditionally.
The notes also mention compound Poisson processes.
Yes. This is an extension where each event in the primary Poisson process triggers an associated random event, often called a jump or reward. The example given was families migrating. Arrivals follow a Poisson process with rate li, and each arriving family has a random number of people, yi. The total number of people arriving by time t xt is the sum of yi for all I from 1 to nt. This xt is a compound Poisson process. We can calculate its expected value and variance based on all and the properties of the family size distribution y.
Like claims arriving at an insurance company, Poisson, and each claim having a random size, the yi.
Perfect example. And Poisson splitting, proposition 5.5 in the notes.
Right.
That's the idea we touched on with coupons. If events in a Poisson process rateless are independently classified into, say, r different types, type j with probability pj, where the sum of pj is 1, then the counting process for events of each specific type forms its own independent Poisson process with rate 1.
So you can split one Poisson stream into multiple independent Poisson streams based on classification probabilities.
Precisely. The application mentioned was modeling employee movement. Maybe employees leave the company, Poisson rate, and they leave for different reasons, retirement, competitor, etc., with probabilities pj. The stream of retirements is Poisson, the stream leaving for competitors is Tresson, and they're independent.
Very useful. And finally, optimal stopping, like deciding when to sell something.
Yes. Imagine offers for an item you want to sell arrive according to a Poisson process over time. Each offer has a random value from some distribution. You have a limited time, or maybe there's a cost of waiting. When do you accept an offer to maximize your expected gain? The notes explore a simple strategy called a Y policy, accept the very first offer that exceeds a certain threshold. Turns out this type of policy is often optimal, and the Poisson process framework helps determine the best threshold, a high, by balancing the chance of getting a good offer now versus waiting for potentially better or worse offers later.
Fascinating. Balancing immediate reward versus future potential, framed by the random arrival of opportunities. Okay, let's shift gears again. The next major topic sounds a bit more abstract, martingales. The notes link this to the idea of a fair game. What's the connection?
That's the perfect starting point. A martingale is a mathematical formalization and generalization of the concept of a fair game. Think about a sequence of bets or observations over time. Let Zn be your fortune, or some observed value, at time n. The process Zn is a martingale if, knowing the entire history of the process up to time n, let's call that history Hn, the expected value of your fortune at the next step, n plus 1, is exactly equal to your current fortune, Zn, formally. EZN plus 1HN equals ZN.
So given everything that's happened so far, the expected value for the very next step is just what you have right now. No predictable gain or loss on average in the next instant.
Exactly. On average, based on past information, you expect to be right where you are after the next step. That's the essence of fairness captured mathematically. The notes give a nice constructive example. If you have any sequence of random variables, x1, x2 bane, and you define Zn as the cumulative sum of the deviations of each y from its conditional expectation given the past. So Zn equals some xi, v xi high 1. Then this Zn process is always a martingale with mean 0.
Ah, so summing up the unexpected parts, the errors from prediction, creates a martingale.
Yes, it centers the process around its conditional expectations.
Now, one of the most powerful results here seems to be the martingale stopping theorem, MST. What does that let us do?
The MST is incredibly powerful. It deals with situations where the duration of the process, the number of steps we take, is itself a random variable. This random duration is called a stopping time.
Okay, what qualifies as a stopping time?
A random variable n, representing the time we stop, is a stopping time with respect to the history hn. If the decision to stop at time n can be made based only on the information available up to and including time n, you can't peek into the future.
So stop after the first time we see 3 consecutive heads, that's a stopping time. Because at any point, we know if we've seen them yet.
Right.
But stop the day before the stock market crashes, that's not a stopping time. Because you need future information.
Exactly. You can't base the stopping decision on future events. Now, the martingale stopping theorem provides conditions under which the fundamental martingale property EZN plus 1HN, EZEN, can be extended to these random stopping times. Specifically, under certain conditions, the expected value of the martingale at the stopping time n, EZN, is equal to its initial expected value, EZZA.
EZN equals EZ0. That seems surprisingly simple. The expected value at a random future time is the same as the starting expected value.
Under the right conditions, often related to the stopping time being finite on average, or the martingale values being bounded, yes, it's a very powerful result. A key application highlighted in the notes is Wald's equation.
Okay.
Suppose you have a sequence of independent and identically distributed IID random variables, xi, each with the same mean, e. Let n be a stopping time for this sequence. Wald's equation, which can be derived using the MST by constructing a specific martingale, states that the expected value of the sum up to the random time n is equal to the expected stopping time en multiplied by the mean of each variable e. So e sum e from I1 to n equals enn.
The expected sum is the expected number of terms times the expected value per term. That feels incredibly intuitive, but proving it requires the martingale machinery.
Yes, the formal proof relies heavily on constructing the right martingale, like sen and a, where s is the sum, and applying the MST. It connects the intuitive result to the rigorous theory. It's used in areas like sequential analysis and renewal theory.
Beyond theory, the notes mention applying martingales to really tricky problems like pattern occurrence times. How does that work?
This is a fantastic, quite ingenious application. Suppose you're observing a sequence of IID discrete random variables, like dice rolls, and you want to know the expected time until a specific pattern appears, say 2, 1, 0, 2.
That sounds hard. Lots of overlaps and near misses possible.
It is very hard with direct combinatorial methods, but the lecture notes describe a clever approach using a fair gambling casino analogy. Imagine a casino where, before each outcome xn is revealed, new gamblers arrive. A gambler who arrives at time n bets a $1 that xn will be the first element of your target pattern, or e.g. 2. If they win, they receive 100 p-dollars, where p2 is px2, and let it ride, betting all of it that xn plus 1 will be the second element. If they win again, they get 1 p2 xn's, and bet it all on xn plus 2 being the third element, 0, and so on.
Okay, so gamblers are betting on consecutive parts of the pattern starting from their arrival time.
Exactly.
Yeah.
Consider the total amount owed by the casino to all gamblers currently active, those who haven't lost yet. This total fortune turns out to be a martingale. Let n be the stopping time, when the entire pattern first completes. At time n, the gambler who started betting exactly when the pattern began will have won a specific large amount, related to the probabilities in the pattern. All other gamblers who started during the pattern's formation might also have won smaller amounts if their starting point matches the end of the pattern. By applying the martingale stopping theorem, EZN equals EZ0, relating the expected total payout EZN to the expected time EN, you can derive formulas for both the expected time EN and even the variance var n until the pattern occurs.
That's really clever, turning a pattern matching problem into a betting game analysis using martingales.
Wow. It's a beautiful example of the power of reframing problems. Martingales also apply to random walks, as mentioned briefly. For instance, finding the probability that a random walk starting at 0 hits a level A before hitting B. Using martingales related to the moment-generating function, like ESN, the notes show how to derive bounds or exact probabilities for these kinds of ruin or boundary crossing problems.
Okay, we've covered a huge amount of theoretical ground probability rules. Random variables, expectations, convergence theorems, stochastic processes like Markov chains and Poisson processes, even martingales. But what happens when the models get so complex, or the real-world system is so messy, that doing the math analytically just becomes impossible?
That's exactly where simulation comes in. It's a crucial tool in the modern probabilist's toolkit. The core idea is, if you can't solve a model mathematically, maybe you can mimic the random process on a computer many, many times. By generating random variables and processes according to the model's rules, you can estimate quantities of interest like expected values, probabilities, variances that are otherwise intractable.
So it's like running the experiment virtually thousands of times and seeing what happens on average.
Precisely. Even something like calculating a complex high-dimensional interval can often be reframed as finding the expected value of some function, ehx, which simulation can then estimate by averaging hx over many simulated x values.
How do we actually generate these random variables inside a computer? We usually start with uniform random numbers between 0 and 1, right?
Yes, computers typically have good pseudo-random number generators for the uniform distribution on 0 and 1. The challenge is transforming these uniform random numbers into variables following other distributions, like exponential, normal, binomial, etc. One of the most fundamental techniques is the inverse transform method.
Okay, how does that work?
The idea is elegant. If you know the cumulative distribution function, CDF, of the random variable x you want, it's called fx, which gives pxax, and if you can find its inverse function, f1u,
The function that undoes fx.
exactly, then you can simulate x by generating a uniform random number u between 0 and 1, and simply calculating x f1u.
Just plug the uniform random number into the inverse CDF. Why does that work?
Because the probability that f1u is less than or equal to some value x turns out to be exactly fx, which is the definition of the CDF for x. It perfectly transforms the uniform distribution into the desired distribution f. The notes give the classic example. Simulating an exponential variable with mean c, the CDF is fx equals 1 exc. The inverse function is f1u, meaning c log 1u.
So x next c log 1u.
Right, and since 1u is also uniformly distributed between 0 and 1 if u is, we can simplify it slightly and just use x next c log u to generate an exponential variable with mean c. It's an incredibly useful and widely used trick.
Okay, but what if finding or calculating that inverse CDF f1 is really hard or impossible?
Good question. That happens often. In such cases, we can turn to the rejection method, also known as acceptance rejection, the core idea. Suppose you want to simulate from a target density fx, that's difficult, but a simpler proposal density gx that you can easily simulate from and which sort of covers fx.
Who covers it how?
You need to find a constant c such that fx is always less than or equal to cgx for all x. Basically, the scaled-up proposal density envelops the target density. Then the procedure is 1. Generate a random value y from the proposal density gx. 2. Generate an independent uniform random number u from 0, 1. 3. Check if u fy, cgy. If it is, you accept y as your simulated value from fx. If not, you reject y and go back to step 1, trying again.
So you generate candidates from the easy distribution G and then accept them with a probability proportional to how much the target density F accounts for the proposal density G at that point.
Exactly. It's like throwing darts uniformly under the curve cgx and only keeping the ones that also fall under the target curve fx. The lecture notes mention a specific rejection method for simulating a standard normal random variable involving generating independent exponentials and checking a condition. It shows how complex distributions can be tackled indirectly.
What about simulating discrete random variables, like rolling a biased die?
The basic method is quite intuitive. Suppose x takes values by 1 by 2, with the probabilities p1, p2, po. You generate a uniform u from 0, 1, then you check. If u p1, set x squared by 1, else if u p1 plus p2, set x squared by 2, else if u p1 plus p2 plus p3, set x by 3, and so on. You're essentially dividing the interval 0, 1 into segments with lengths p1, p2, p3, and seeing which segment u falls into.
Okay, straightforward comparison with cumulative probabilities. And specific discrete distributions might have shortcuts?
Yes. For geometric distribution, number of trials until first success with probability p, the notes mention it can be simulated using x, 1 plus log u, log 1p, where yo's is the floor function, greatest integer less than or equal to, a direct formula. And a binomial NP variable, number of successes in n trials, is easily simulated just by its definition. Some n-independent Bernoulli trials, so generate n uniform u's and count how many are less than p.
Simple and direct. Now, simulating those non-homogeneous Poisson processes where the rate t changes over time, that sounded tricky because the nice exponential time between events property breaks down.
It does pose a challenge. Standard methods don't directly apply. One very clever approach described as thinning, sometimes called sampling a Poisson process.
Thinning, how does that work?
The core idea: 1, find a constant rate, lambda star, that is greater than or equal to your non-homogeneous radial for all times t in your interval of interest. So STOI is an upper bound on the right. 2, simulate a homogeneous Poisson process with this constant radial. This is easy using the exponential inter-arrival times method, mean 1. Let the arrival times be t1, t2, t3. For each arrival t generated from the homogeneous process, calculate the acceptance probability, PTI, for generate an independent uniform u from 0, 1. If u APTI, then you accept t as an arrival time for your non-homogeneous process. Otherwise, you reject or thin out t.
Ah, so you generate potential events at the maximum possible rate and then probabilistically keep them based on how the actual rate compares to the maximum rate at that specific time.
Exactly. It's remarkably elegant. You create the complex process by selectively keeping events from a simpler, constant rate process. And the notes mention you can optimize this if a TT has different upper bounds over different time intervals, using piecewise constant low values to reduce the number of rejections and make it more efficient.
Very clever. Finally, the notes touch on variance reduction techniques. Why are these needed? Isn't just running the simulation longer always an option?
Running longer helps, but variance reduction techniques aim to get a more precise estimate for the same amount of computational effort or the same precision with less effort. They make simulations more efficient. One technique is antithetic variables. Suppose you're estimating x1, xn, where g is a monotone function, mostly increasing or mostly decreasing. You generate your random inputs using uniform variables, u1, all day. Instead of doing a second independent run with new uniforms, you do a second run using 1u1, 1, 1, 1 as your inputs. Since u and 1u are negatively correlated, if g is monotone, the outputs gu1 and g1u1 will also tend to be negatively correlated. Averaging these two negatively correlated runs often results in a final estimate with much lower variance than averaging two independent runs.
Using the opposite random numbers helps cancel out some noise.
That's the intuition. Another major technique is importance sampling. This is especially useful when you're trying to estimate rare event probabilities or expectations dominated by specific regions. Instead of simulating from the original distribution fx, you simulate from a different proposal or importance distribution gx that puts more emphasis on the important regions where fx is large or where the function you're averaging, hx, is large.
But doesn't simulating from a different distribution give you the wrong answer?
You have to correct for it. If you simulate y from gx, you estimate the original expectation EFHX by averaging the quantity HY, FY, GY. That ratio, FY, GY, is the likelihood ratio or importance weight that corrects for sampling from G instead of F. If you choose G cleverly such that the weighted value HY, FY, GY, has much smaller variance than the original HX, you can get a vastly more efficient estimate, especially for rare events.
So you bias your sampling towards important areas, then correct with weights. Powerful stuff.
Very powerful. These techniques are essential for making complex, large-scale simulations feasible and reliable in practice. Hashtag tag tag outro.
Wow, what a journey that was through these lecture notes on probability. We really covered a lot of ground. We started with the absolute basics, the language of chance sample spaces, events, basic probability rules.
Setting the stage. Then we moved into conditional probability and the power of Bayes' formula for updating beliefs based on evidence.
Right, reasoning backwards from observations. Then we quantified randomness with random variables, defining expectation, the average, and variance, the spread.
And we hit those major theorems, the central limit theorem, explaining the ubiquity of the bell curve, and the strong law of large numbers, guaranteeing long-run convergence to the expected value.
Then we dove into processes evolving over time, stochastic processes in general, and then the elegant memorylessness of Markov chains with applications from genetics to random walks.
Followed by the incredibly versatile Poisson process, counting random events in time, its deep connection to the exponential distribution, and its use in everything from coupon collecting to optimal stopping.
And let's not forget martingales. Formalizing fair games, the power of the martingale stopping theorem, and that ingenious gambling analogy for solving pattern occurrence problems.
And finally, we saw how simulation brings all this theory to life when analytical solutions fail, using techniques like inverse transform, rejection, thinning, and variance reduction to explore complex systems computationally.
It's really clear this isn't just abstract math locked away in textbooks, is it? Whether you're making financial decisions, trying to understand how diseases spread, designing more efficient systems in engineering or logistics, or even just trying to get a better handle on the odds in a game, these tools, these ways of thinking, are constantly at play.
Absolutely. They equip you, the listener, to think more critically about uncertainty in all its forms, to make more informed choices when faced with randomness, and maybe even to see the hidden structures and patterns underlying the apparent chaos of everyday life.
And here's a final provocative thought for you to mull over, something building on what we've discussed. We've seen repeatedly how the average behavior of random phenomena often converges to something stable and predictable thanks to the law of large numbers, the central limit theorem, steady state probabilities, and Markov chains. These give us a sense of long-run order.
Predictability emerges from randomness in the long run.
But what about those truly rare, unexpected events? The black swans that seem to defy the models and averages? Probability theory can assign them a likelihood, often very small. But these notes remind us that the unexpected, the improbable, is always a part of the sample space. Its probability might be tiny, but it's not zero.
That's a crucial point. The models account for them, but their impact can be disproportionate.
So the question is, how much of our planning, our decisions, our view of the future should be guided by the expected, the average, the predictable convergence? And how much focus should we place on preparedness for the improbable, the outliers that lie waiting in the tails of the distribution? Where's the right balance?
That's a deep question with no easy answer, touching on risk management, resilience, and how we fundamentally deal with uncertainty. This deep dive has hopefully armed you with a powerful new lens. Keep exploring these ideas, keep questioning, and keep diving deep.